Well, hello everyone. Welcome to this Wind Power Engineering and Development webinar, Actual Costs versus Energy Loss, Meeting the Challenges of Electrical Transmission. I'm your host, Paul Dvorak, editor of Wind Power Engineering and Development magazine. Thank you for joining us. Just a brief agenda before we start. This webinar will be available at windpowerengineering.com. A link to it and all those slides will be emailed to everyone. At the end of the presentation, we'll have a brief question and answer session. Of course, not everyone that wanted to watch today's webinar could be with us, so you can help them learn from it by tweeting key points and takeaways that you think important. In your tweets, be sure to include the hashtag WindWebinar. Now, after the presentations, I'll read the questions that you and the audience have submitted. And you can do that by typing them into the questions box on your GoToMeeting panel that should appear to the right of your screen. Now, I'd suggest not waiting to the end of the presentation. Type the questions in as they come to you. And we'll try to answer as many as possible before our hour is up. Now let me tell you a little about our speakers, and then I'll turn the microphone over to them. Our first presenter is Brandon Goltz. He's the design engineer in generation planning and renewable energy at ULTIG. The company was founded on the idea of bringing electricity to the rural Midwest, and it continues to embrace that responsibility through changing times and technologies. Brandon is responsible for all aspects of electrical engineering projects, from construction cost estimates to writing specifications and project management. For the past 4 years, Brandon's been involved in the design of electrical distribution systems for wind farms, campuses, and some substations. He's also a graduate of North Dakota State University with a Bachelor of Science degree in electrical engineering. Our second presenter is Pierre-Marc LeBlanc. He is a product engineer with General Cable, the BICC Brand Electric Utility Products team, headquartered in Highland Heights, Kentucky. General Cable develops, designs, and manufactures copper, aluminum, and fiber optic wire and cable products for the energy, industrial, specialty, construction, and communications market. With 8 years of experience with the company, Pierre-Marc has held positions from process engineering to design engineering and has been responsible for managing cable design systems. He provides application engineering tech support and designed low voltage and medium voltage power cables to meet the needs of electric utility specifications. Pierre-Marc is a Bachelor of Science graduate of École Polytechnique of Montreal in electrical engineering. And he's also a member of IEEE and the IEEE PES Installation Committee, Conductors Committee. And with that, let's start with Brandon Goltz. Brandon, the microphone is yours.
Thanks, Paul. Today I'd like to just touch on some topics that will give you the different factors that electrical engineers will have to consider for reducing the costs throughout a wind farm project. Costs specifically affecting energy losses and installation costs. Whether you're an investor, or engineer, a client, or even a contractor, you should be aware of some of how these different aspects of a project and how these requirements will affect energy losses and project costs. The main points of these webinars focus on the conductors and the transformers and the costs that are associated with them. Just a little bit of background again. My name is Brandon Goltz and I work at ULTIG. Our company is a consulting firm for energy services, building services, and civil services, as well as land services. We're 100% employee owned, and we've been ranked 207 on the top 500 engineering design firms by the nation by Engineering News Record. We have offices throughout the U.S. here, and they're located in Fargo, Bismarck, Williston, Detroit Lakes, Minneapolis, Sioux Falls, Denver, and Cedar Rapids. Our company has kind of been in the wind farm industry for right before it got real big, and it's kind of interesting fact that our companies have helped design over 6 gigawatts worth of wind power projects in approximately 15 states and Canada. And here's a map of the U.S. and Canada showing locations of most of the projects that we've helped engineer. So I want to start by showing a typical example of a small wind farm. And this layout is just to kind of help you see the basics of a wind farm and what areas in which we can help reduce losses. So starting from the top, the transmission lines that are connected from the grid go down to a substation transformer. And this substation transformer is generally steps up your voltage from 34.5 kV to 69 kV to approximately 345 kV. The extreme high voltages help with energy losses through the transmission line. That's also one area you can look at your conductor, as these transmission lines flow miles and miles to get to where they need to go in order to distribute power to everyone. Going down further, the substation has 3 feeder breakers in this example. These feeder breakers help protect the wind farm for the 34.5 kV collection feeders. Each feeder breaker contains an effectively grounded system device, typically. This can be either a grounding transformer or a grounding breaker. Going down a little bit further, you can see the wind turbines are connected to a generator step-up transformer. The generator step-up transformer is a key aspect of where you can save losses too. Depending on the turbine type on which you're installing, these generator step-up transformers are either located up top in the nacelle of the wind turbine tower, or they're located at the base of the wind turbine. One more aspect is the underground cable. This is one of the easiest examples of how you can help reduce losses, and this is what I really want to specialize in, as I'm typically designing most underground collection systems. So to look at the other areas of where you can reduce losses is the transmission line, the grounding transformer, generator step-up transformer, and the underground cable. And these are the 4 areas that I'm going to look a little bit more into in this presentation. So I'd like to start out with looking at the underground versus overhead option. Typically, a wind farm would have underground for the collection system, but I have seen it used as overhead. One of the benefits of having overhead is the conductors can actually take a lot more power flow than underground. This is simply due to they're suspended in the air and they have a lot more cooling effects versus having them insulated and buried under the ground, as heat is the biggest factor for how much power can flow through these conductors. Although the overhead can offer a cheaper installed cost over really long distances, you're still going to need underground to connect to each turbine. Overhead also has issues with landowners because they sometimes don't like these structures on their properties. Overhead also presents more logistical problems like construction crane paths, operation maintenance problems from animals or environment. With overhead, you still have issues with storms when they come through and can knock out the power lines. This can sometimes be easily seen by someone visually inspecting them, versus if there's an underground failure, they would have to excavate and find the problem with other means. One last thing to look at for overhead conductor is if you have a tremendous amount of overhead line, we've seen typically in wind farms that it introduces reactive power needs throughout the wind farm. And depending on your interconnect requirements, this may have a need for additional cap banks to compensate for that. With underground cables, we don't see this happen as often, as they tend to be more capacitive than overhead cables. Change the next slide here, and the underground installation can improve aesthetics versus your overhead because it's buried in the ground. Underground cables typically will have less losses than overhead conductors, but they cannot carry as much power from the heating effects I had explained earlier. If properly installed, the weather and storms and ice and snow and sleet don't affect the underground quite as much as the overhead conductors. And I'd like to talk about the two most common types of underground cable insulation used in these wind farms and throughout the industry. The two types are EPR, which is an ethylene propylene rubber. This type of material, it can be described similar to an eraser, and that's what is insulating the conductor from shorts and whatnot in the ground. The other type of insulation is an XLPE, which is a cross-linked polyethylene, and it's very similar to a hard malleable plastic type material, if you're not familiar with it. The differences between these two materials is EPR has been around a lot longer. This type of insulation tends to have a higher loss, but the advantage of this type of insulation is you can run the cable to a hotter temperature, 105 degrees C, versus XLPE tends to be 90 degrees C for its maximum operating temperature. The XLPE type insulation has a extremely decreased dielectric loss compared to the EPR. So using an XLPE insulation can help your losses over time. So now, copper versus aluminum. For years, copper has been the king for electrical conductors. But as the cost of these metals have increased, aluminum has stepped in and filled the shoes of copper. Although these two metals differ in many different properties, as you can see on the slide, I've shown aluminum is the most abundant. It's 61% the conductivity of copper. So that means if you have a copper cable with a same size diameter as a pure aluminum cable, you're going to be able to carry tremendous more power through the copper versus the aluminum. This is the major advantage of copper, is just more conductive. Over the years, people have had shied away from aluminum just because the properly making connections on aluminum is more difficult. One of the main things that you need to consider is properly cleaning before making splices or connections throughout the wind farm. You also need to consider expansion rates when you're connecting aluminum versus copper. These two metals don't like to be connected to each other. They have a type of chemical reaction that goes on, and also they have different expansion rates as they heat up. And this tends to be problemsome. So there's been ways around this where a transition metal has been used, such as tin, or the copper is made with aluminum, like a copper-clad aluminum. Upsizing the minimum size aluminum conductor can sometimes offer a much cheaper method of energy loss reduction instead of reverting to copper. The benefits of having a larger diameter cable conductor is that the heat can be dissipated faster over a smaller area. Kind of acts like a small radiator, if you will. While both metals have a corrosive issue in the environment, oxidation occurs, on both copper and aluminum. The one thing about aluminum is the oxidation almost creates a thin layer of insulation around the metal. And that's why you never see copper used in grounding situations, because the grounds are directly exposed to the elements. That's why copper is always used in grounding situations. So the next area I'd like to talk about is the concentric neutral wire sizing. These cables that we're using are typically 35 kilovolts, or 34.5 to be exact, and they have the conductor in the middle there, as you can see on the slide, with a shield and insulation. There's an insulation shield, and then there's these concentric neutral wires that surround it. One of the areas you can help decrease losses is change these concentric neutral wire sizes so you can minimize the losses on these particular wires. The losses are generated from the current that's induced on these concentric shield wires or concentric neutral wires. And if you can size your cable appropriately, you can save losses by reducing these number of cables. The drawback of decreasing the concentric neutral wire sizes is that you'll have to make sure your fault current at your wind farm is low enough so your cable won't be damaged during the fault. So now I'd like to talk a little bit about economic cable sizing. When you upsize conductors, it can be an effective way at reducing energy loss throughout your wind farm. Even small wind farms can have a lot of cable. We had a very small wind farm that had approximately 25 miles of 34.5 underground cable, and the losses were almost half just from the cable. So it's a pretty significant portion of the losses throughout the wind farm project. We like to give our clients an option when we're designing these wind farms. And this slide kind of shows you there are 4 different options that were looked at. The options 1, 2, and 3 show a collector system of buried underground 34.5 collection cable that was all laid in the same row. So it's the same trench. The only differences between options 1, 2, and 3 are the amount of turbines on a particular size cable. The owner had his own scheme that he wanted. We sized the absolute minimum size cable that you could possibly use for the amount of turbines on each one. And then we started upsizing the cables that have a tremendous amount of loss on them, which we would call the economic cable sized. And option 4, just to show comparison, was the landowner had a route change because he didn't like his cable, the cable in his yard. So we had to do some adjustments on there, and it's kind of neat to see the results on that on this slide here. So the cable energy losses only, and this is just the losses on the cable, are shown in the chart on the upper left. You can see that option 4 has the least amount of cable losses. However, if you look on the bar graph, it actually costs the most to install. And if you look at the complete opposite, the one that's the cheapest to install, option 2, has the highest losses. So what I'm trying to get is, how do you compare losses versus installation costs over time? And this next slide helps show that. So for trying to utilize engineering economy, we can use a present value function in order to assign the losses that you have in your wind farm to a dollar amount. These annualized losses can then be moved to the present, and the installation costs can be added to it, giving you a total present value of your wind farm. There are a lot of things that in the wind farm, the installation costs would be the same, such as your elbows and all your goods that you need, that you're going to need in every single option. So a lot of that can be taken out to make your calculation more simplified. As you can see from this, option 3 ended up being a little bit better than the owner's option, and which we proved to him using some key pieces of information using present worth analysis. We typically would like to receive a lifespan of the wind farm, a percentage rate of return, and also the cost of the power that they're going to be selling it at. And then we compare this to the cost of the cable, or the installation cost of these cables. So this was one good way of showing how you can decrease energy loss but still increase the installation costs, and over time it's actually a cheaper option. So transformer types. There are a lot of different types of transformers. I'm going to touch on a few that are very common to the wind farm industry. Dry type transformers they're usually provided by the turbine manufacturer because they're put inside the nacelle that's up on top of the tower. These tend to be beneficial because the power is immediately transformed to the higher voltage, like the 35 kV, and that 35 kV runs down the tower and out to the collection system. This particular voltage actually helps decrease losses. The only issue is that dry type transformers tend to be a little bit more lossy, so there's a little give and take on which particular transformer is actually better when you consider the different types. Oil-filled transformers, these are the transformers you see with the fins. Both of the ones pictured in the slide right now are the oil-filled type. These units tend to be cheaper. They're less expensive, and they have shorter lead times. Sometimes the no-load losses can be specified to be in certain amounts based on your manufacturer. And this can result in a very cost-effective option while still keeping the no-load losses in check. Another type of transformer is the amorphous core type transformer. And this particular transformer has a very unique metal that's used in the transformer, which decreases the no-load losses. They tend to be a lot more expensive, but if you think about a wind farm, it's not windy all the time. Half the time the wind farm is not blowing, these transformers are actually being energized by the system and having losses built up on them. So the amorphous core transformer decreases that tremendously. Another thing you can consider within all these types of transformers is aluminum versus copper again. There are many manufacturers who have different designs and different ways of doing things, especially with the transformer core type. Significant benefits is aluminum can be lighter, but the transformers are going to be larger. Copper is obviously going to be heavier, but it's going to be smaller. So, depending on the market, aluminum may be cheaper versus the copper too. So just some more things you want to consider. Most wind farms run up on a delta system. So when the feeders have some sort of issue and a fault, they'll have to have their substation feeder breaker protect them and turn it open. And it seems like the transformers or the turbines can produce power a little bit longer, and this causes a voltage rise on the system. So a typical wind farm will either have a grounding breaker or a grounding transformer. Normally they can be located within the substation. Well, the differences between the losses aspect of these is the grounding transformer is going to have no load losses all the time. A grounding breaker or grounding switch, it won't have any losses because there's no transformer there. Just another thing you can consider. So basically, I went over a very few points for looking into losses versus cost of a wind farm, and discussing the different conductor types, transformer types, and choices in copper versus aluminum. Hopefully, this will give you a little bit better knowledge and understanding of all the different aspects of where the money and the design is going to. With this, I'd like to hand this back off to Pierre Marc, and he can talk about the underground cables a little bit more.
All right, thank you, Brendan. So, hello everyone. So my name is Pierre Marc Leblanc. I'm a product engineer for General Cable, working in the utility product engineering team. So today here in my presentation, I'll be talking about medium voltage power cable designs used in the collection system, and more particularly about cross-linked polyethylene jackets. So first, I'll give a brief overview of the various cable constructions that are being used on a typical wind farm. We'll then review the design features of choice for the medium voltage power cable used for the collector system. Then we'll also talk about a little bit more about the different insulation materials and their characteristics and how they influence the dielectric losses. And finally, we'll talk about the benefits of using the cross-linked polyethylene material as a jacket, and then I'll explain how the cross-linked polyethylene and its enhanced resistance to deformation can offer benefits and allow for even further optimization of the concentric neutral sizes, which will then provide better efficiency over the life of the cable and then lower line loss. And then we'll also take a look at a case study and just in the impact on copper content for various typical wind farm cable construction. So here's an illustration showing the different applications in a wind farm where there are various wiring cable constructions that are being used. There are numbers of cable design used starting in the nacelle, then the tower, and then the collection system. There are also substation and transmission cables and conductors, as well as grounding conductors. So here in this presentation, we'll pay a particular attention to the medium voltage design used in the collector system. So first, starting with the nacelle. So in the nacelle, there are varying designs that vary from electronic, power, control, fiber optics applications. These generally correspond to small dollar value or highly specialized cable. The applications require really highly flexible cables. These are also generally OEM type and then supplied by the turbine manufacturer. Then in the tower, again, flexibility is very important. Then also, as Brendan pointed out, there's some consideration made to the ability of moving the current down with as little loss as possible. Here, depending on the turbine manufacturer design and where the transformer is located, up in the nacelle or down at the bottom, then a medium voltage or low voltage flexible cable is going to be used. Then to maximize flexibility, typically soft annealed copper flexible stranding are going to be used. And the flexible medium voltage cable is typically a 35 kV design similar to like a mining cable or SHD portable power cable designs. On the low voltage, would typically use the 2000 volt DLO EPR cross-linked CPE insulation jacket design. And then when a low voltage flexible cable is used to make the connection from the nacelle, then to the first tie point up in the tower, then from there, an aluminum building wire design would then normally be used to connect the wire down from that point. And again, those constructions normally would be typically specified by the turbine manufacturer. So here then in the now going to the collection system cables. So the 35 kV design portion is one of the most critical aspects of a wind farm project. So the cable design used is typically a 35 kV TRXLP insulated URD cable with concentric neutrals. So the TRXLP insulation offers a high dielectric strength and it has the lowest dielectric loss characteristics of any other medium voltage cable type or insulation type. Now I'll review in a little bit more detail later the dielectric losses characteristics and the different type of insulation material. But then for mechanical protection, there's an extruded to fill polyethylene jacket is used to provide the toughness to withstand automated trenching and then for direct burial application. Then the size of the concentric neutral is normally designed to meet the fault current needs at each specific wind farm project, and then again to minimize the shield losses. Again, those designs have an accepted long history of performance and reliability within the utility, and then has been adopted as the preferred design used for the 35 kV cable portion of the collection system. And then for transmission product, again, these can be either overhead or underground insulated cables. There's a numbers of different overhead conductor designs that are available, ranging from ACSR, aluminum conductor, steel reinforced, or ACSS, aluminum conductor, steel supported conductor using soft and aluminum wires, providing improved thermal capabilities with the conductor. Other products such as ACCC, aluminum conductor composite core, or T2 twisted pairs, or trapezoidal wire designs can also be used. Those more specialized construction can offer various benefits ranging from higher impactity rating, smaller diameter, or better thermal characteristics. And then on the underground side, high voltage, extra high voltage cables, normally ranging from 69 to 500 kV, can also be used. These would normally involve a turnkey project where complete engineering and installation services are provided with the cables, terminations, and joints. Then there's a number of other constructions such as low voltage power control, medium voltage, instrumentation cables, as well as supervisory control data acquisition systems that are used in the substation. All right, so here looking at in more details at what are the critical design features of the medium voltage power cable that is used in the collector system. So first, I would say it is important to utilize a design that has been qualified to the NCI-CEA and then AIC-CSA standard and specification, and that the material is also CSA or UL approved. It also ensures that all the materials and cable design have been tested and then certified to the applicable North American industry standard requirements. Then as also Brandon was talking about when it comes to the conductivity versus the economics of aluminum versus copper conductor. So aluminum conductors is really the material being used. It is the primary material being used for underground residential distribution cables by the utility, again, because it's what makes the most sense as far as cost of the metal versus the conductivity of the metal. For utilities, they will use copper conductors in an area where they really require either higher impacities or cable will be installed in conduits, and then you're limited with the dimension. For that application in the wind farm, there are buried application when aluminum conductors, that's typically for what makes the most sense in the collector system. And then the use of water block stranded conductor, again with a size of the conductor ranging from the 1 up to the 1250 kc mil, would prevent longitudinal water penetration along the length of the stranded conductor and then extend cable life. Benefit of using, again, water block conductor, something has been demonstrated using ACLT, actually cable life testing. And then on the material, clean materials, dedicated clean rooms, enclosed material handling system, ensure protection of the semiconducting shield, and then insulation compounds from the external contamination. And then for the insulation, we talked about it already a little with the tree retardant cross-linked polyethylene. So it's tree retardant will ensure good retention of the electrical properties in a wet environment from a long-term cable life. And then it's material that has a very low dielectric losses compared to the other medium voltage insulation material. It also has the benefit of being translucent, which allows for ease of monitoring cleanliness of the compound through like optical pellet inspection or oil examination of cable sample. And then water blocking components in the metallic shield with the extruded to fill jacket that prevents the longitudinal migration of water under the jacket if water gets in through damaged portion of the jacket or through the splice. So here going to the insulation materials. So in North America, there are primarily two main types of insulation material that are used for medium voltage cable, power cable application. There are the tree retardant cross-linked polyethylene and then EPR, as again Brendan was pointing out. So EPR are typically formulated and combined by the cable manufacturers. So there's a numbers of different EPR materials that are being used. But you can generally classify them in two different types of material. or type of formulation, semi-crystalline or amorphous material, and then this will have an impact on the resulting dielectric losses, where amorphous EPR having a higher dissipation factor will generate even more dielectric losses than semi-crystalline EPR. But then in this table, you can easily see that the comparison of the EPR and the dissipation factor characteristic and associated dielectric losses of each type of insulation, that the EPR versus TRXLP, that it demonstrates well that TRXLP insulation has a much lower losses than any EPR. And then TRXLP provides then a lower, typically a lower purchase cost and then lower operating expense than EPR. Then again, worth to note that both materials have good tree retardant properties, which will ensure, again, reduction of water tree growth within the insulation and then retention of the dielectric strength of the insulation material. Here's just another way, a little bit more graphical, of looking at the comparison between dielectric characteristics and losses of the different type of insulation material. So these losses are, in the second graph to the right, are translated into annual costs in dollar per 100 miles of cable, calculated for different rates. So again, it quickly at a glance show that the advantage of using TRXLP insulation to, again, reduce the electric losses within the collector system. So now we'll talk a little bit more about the jacket and then the use of cross-linked polyethylene material as a jacket for the medium voltage collector cable. So it's circular or linear low density LLDPE material has been the thermoplastic jacket material of choice for North American utility for medium voltage primary distribution cables, primarily because of its good physical properties and relative low cost. So it is a material that is compatible with the extruded semiconducting insulation shield. It's normally applied as an extruded to fill jacket encapsulating the neutral wire. So this allows for a robust design that can be easily sealed for longitudinal water penetration resistance. So here we'll talk about the cross-link polyethylene jacket, and then the additional benefit that, in addition to having maintaining equivalent physical properties to the existing LLDP jacket construction, then the additional benefit that it provides on the enhanced thermomechanical properties, reduced copper and concentric neutral, and then allow for cooler operation, optimized efficiency with lower line losses. So the XLP jacket, again, will maintain equivalent physical properties to the existing LLDP jacketed construction and improve the thermomechanical properties of the material. So we have completed various testing, such as abuse resistance testing, including crush, impact, abrasion, puncture resistance. Also completed jacket stripping, coefficient of friction, flexure property, and compared the XLP material performance to the existing LLDP jacket material. And then the test data has shown that the XLP jacket maintains these properties and insulation characteristics. And then on the other hand, then you improve the thermomechanical property of the material by adding a thermoset material. So also noted that in the past XLP materials required to be manufactured and cured on the CV line, so it was not possible to apply an XLP jacket due to, again, the problems of passing the insulated core with its metallic shielding into the CV line. Now with the newer, more secure XLP material technology, it is now possible to apply a jacket, this kind of jacket material, using the same type of extrusion line than applying an LLDP jacket. But it also has a proven technology used for many years for low voltage XLP insulation cable. So the enhanced mechanical properties of the of the XLPE jacket and have been demonstrated through the NCICA thermomechanical qualification testing. Also, the XLPE jacket material is tested at higher temperature for heat deformation during the production testing of the cable. Here, that's the pictures that shows the test set for the thermomechanical qualification testing of NCICA and AIC. So this test is performed on a cable in a conduit. The conduit consists of two straight sections in the U-bend, and the testing that is outlined in the industry standard is normally done on a one conductor single cable construction. Here we also evaluated the performance of a three cable installed in a trefoil arrangement. So the test protocol there consists of 14 current load cycles. So during the 6-hour on period, the cable reached emergency overload temperature of 140 C degree for 105 rated cable, and then return to 5 degrees C of ambient temperature during the off period. And then you measure the initial and final dissipation factor, and do partial discharge testing is completed. Then dimensions are reviewed from sample taken from the U-bend, and the cable shields and jacket are inspected. Then they must not exhibit any cracks or splits. You would typically qualify the test samples. The size of the test sample would typically be a 500 kc mill, 35 kV aluminum construction, and with this size you would qualify the complete range of the product size. Then you have to qualify each type of construction, like combination of TRXLP insulation with concentric neutral with extruded to fill P jacket. So here we ran some comparative testings on this size with extruded to fill thermoplastic P jacket compared to extruded to fill thermoset XLPE jacket. Here are some pictures that show the results of the first testing completed with the thermoplastic LLDPE jacket. As you can easily see in the pictures, that the jacket exhibit clearly exhibit melted spots, and also on the trefoil construction, the jacket is fused together, and even in some areas it caused exposed concentric neutrals. Then when you compare the testings on the XLPE jacketed cable, then you can see that the cable maintains integrity and can easily pass that type of cyclic aging and thermomechanical views. So the enhanced properties and the better heat deformation of the jacket of the XLPE jacket, in the end, what does it provide? So it's again, when Brendan was talking about minimizing losses and then optimizing your design and your neutral size to minimize the losses, then with an XLPE jacket you can go even further and then even further optimize the size of your neutral, and then even achieve bigger, even larger saving on losses. So typically the cable are designed to meet the requirements of ICEA P45 482 to calculate, and how do you calculate your required cross section of your shield to meet the given fault current. So for thermoplastic LLDP jacket, they are limited to a maximum transient temperature of 200 degrees C, where with a thermoset XLPE jacket, the standard allowed to go up to 350 degrees C. So the way this is calculated is that you start with your normal rated operating temperature of your cable based on that, so it's 90 or 105 C, depending on how you design your system, and then you start at based on that temperature, you have a given neutral temperature, and then what you measure is the amount of copper that you need in the neutral to be allowed to sustain the temperature rise for certain fault duration without damaging the cable core or the jacket, maintaining the integrity of the cable. So with the XLPE jacket and its it's better heat deformation, then the same neutral can go to much higher temperature without damaging the cable, as it was demonstrated in the thermomechanical testing. So the higher temperature allowance of the XLP jacket provide for an equivalent current capability with reduced neutral than minimizing the required copper in the cable design. And also in turn mean smaller neutral means higher shield resistance, which means smaller circulating current in the metallic shield, which may also even help reduce the operating temperature and have also a positive impact on the resulting ampacity of the cable, and then reduce the losses in the metallic shield. So I'm just trying to go up. Sorry, a little bit of lag to move between slides. So on the next slides, here I'm going through like typical various sizes of typical wind farm cable construction, and then going through the again just more visually showing the impact on the reduction in copper content into the concentric neutral. So here you can see that it will definitely have, like when in terms of this, will definitely have a much bigger impact on the larger size. But when it comes to even the smaller conductor size, which have normally the larger neutral in terms of conductivity related to the face, then you will still have some significant savings. Also, if it's also even just in copper content and upfront cost, and going with the reduced neutral design with the XLP jacket. So in general, with what you can achieve is approximately 25% in reduction in copper in the concentric neutral. Here, what I'm showing is just a small, quick comparison, picking up one of the larger size used in the wind farm, the collector system. So based on 1,000 kcm aluminum TRXLP 35 kV cable, 1/3 neutral. So we're comparing based on that 1/3 neutral 20 number 10 with XLP jacket. We're comparing the copper content and then also the shield fault current. So then with an XLP jacket, you can change and optimize your concentric neutral while maintaining the same shield fault current capability. And as you can see, the impact on reducing the amount of copper in the neutral is significant. There's also a little bit of a positive impact on the ampacity of the cable. And then here, based on the 20 circuit miles of the cable over a 20-year life of the wind farm, they're just estimating what would be the cost of the dielectric losses in the cable, so the operating expense, and then just comparing again side by side, and then what would be the calculated saving over like a 20-year span. That's so that concludes what the presentation that I have for today. So Paul, back to you.
All right, thank you very much, gentlemen. You know, as a mechanical engineer, I find the discussion of electrical topics fascinating. I get to look at the mechanical stuff in the nacelle, but not too often the electrical stuff. So this is good, very good. Okay, I see we have a few questions, and we can get those now. I want to remind viewers that they should type your questions into the question box on the right of the screen, and then I'll ask our presenters. Let's start with one for you, Brandon. Okay, how do you come up with the requirements for the economic analysis? For example, for lifespan, for rate of return, or for cost of power?
Well, for the lifespan, rate of return, and cost of power, we'll typically work with the owner, the investor, or the person you know, in charge of putting up this wind farm for selling, maybe even. And we'll work with them and typically come up with a number that they're okay with and that works good. And what we've seen typically is for rate of return is around 6 to 8%. And the going rate for power is typically $70 to $85 a megawatt hour. and the lifespan for a typical wind farm is 20 to 30 years.
Okay, very good. All right, here's one for you, Pierre LeBlanc. Pierre-Marc. It's a little bit long, so let me read it here. Are the cable handling and installation techniques different with a cable jacketed with a cross-linked polyethylene compared to a thermoplastic LLD-PE jacketed cable?
No, there's for the end users, the person who's going to install and manipulate those cables, there's really no difference. And the way the material was formulated was that it would add similar physical properties and with the enhanced thermomechanical performance. So from a material handling and the way you prepare the cable, the way you strip the jacket, there's really no difference at all.
I see. Okay, so the handling is the same despite the different material, the improved material. Okay, very good. I have a question for you, Brandon. In one of your earlier slides, you showed some transformers, and I think it was a series of 3, and one of them was an oil-filled transformer. They require some maintenance. What kind of maintenance does an oil-filled transformer require?
Well, typically an oil-filled transformer will have dissolved gases throughout its lifespan within the insulating oil. And these dissolved gases will actually change the properties of that oil, and maintenance crews will go out, normally it's annually, and test this. There's a specific test they can do to check this oil and make sure it's still in the proper working order. Sometimes they have to actually fill it up if they're leaking too. So
I see.
There's a couple different things.
I see. That could be problematic. Yeah. Okay. Very good. Pierre-Marc, I have another question for you. What's the design life of the 35 kV TRX PLE concentric neutral power cable designed for use in the collector system?
We're typically looking at 40-year life. Now again, this is a value that's even been there used in the industry for this cable design for a little while, and now with there's even even more recent improvement in cleanliness and material handling, and then with strain fill material, water block conductor, and all the good things that we talked about when I said some of the things that are like the important features for the critical features for the medium voltage cable. I would say now none of those recent with modern technology cable have been installed long enough in the ground to come up with a higher number, but I would say at least a 40-plus year.
40-plus years. Okay, that's quite a while. I guess we'll have to build a second wind farm then after the first one wears out. Okay, one more question for you, Brandon. How do you come up with an X-sized cable scheme?
Well, there's 2 ways that we've been able to do this. One way is, in both ways you have to build a model. Typically we use an electronic software program that designs designed to model the cables and energy loss. You can go through and run your scenarios and increase the cables that have a larger loss on them. This typically is the heavier loaded cables, the ones that have more turbines on them, or longer runs. Another way that we've done it is you take an average cable length and adjust the power through it. By adjusting the cable size, you can come up with a most optimized cable size for how many turbines are on there, and then using the cost of the conductor, you can judge which cable is the best for your wind farm.
Well, it sounds like you're modeling the whole wind farm, like the electrical characteristics of it. Is that right?
Exactly.
Oh, I see. So you can play some what-if games with that too, then.
Yep. There's a lot of that going on too.
And the money, the cost calculation is one of the results. So I see. Okay. All right. Well, that was all the questions. Anyone else? I see. All right. Well, once again, this webcast will be available at windpowerengineering.com. You see on the final screen there's some contact information. And one final message, you can follow Wind Power Engineering on Facebook, Twitter, and LinkedIn. This concludes our presentation. I'd like to thank everyone for their attention. And from the staff here at Wind Power Engineering, we'd like to wish you a good and productive day.